The desert morning was brittle with silence. The scrubland stretched for kilometers, dotted with low ridges and rocky outcrops, each shadow sharpened by the pale light of early dawn. A faint trace of smoke curled over a ridge, almost imperceptible against the cold blue of the sky. The soundscape was minimal. Distant wind over sand, a bird's cry somewhere beyond the rise, the faint mechanical whisper of arriving support vehicles. Scattered across a rocky depression were fragments of a once sleek fuselage. Panels, bent and scorched, lay in silent testimony to the forces at play. No flames remained, no chaos, only the cold geometry of metal twisted by speed and impact. Each fragment suggested a sequence, a chain of events whose final link would never be forgotten by those who would reconstruct it. The A-Force response arrived methodically. Soldiers and technicians, faces solemn, moved with purpose. Their eyes traced the arc of the wreckage, noting orientation, distance, and trajectory. The land itself was telling a story. Craters, ground scars, a telltale smear of paint across the rocks, but it spoke only in observation, not judgment. Above, the pale morning sky offered no explanation. Radar signals would later confirm a routine training sortie, one that began with normal flight checks, steady climb, and calculated maneuvers. Within minutes, the flight envelope had been exceeded, unknowingly, invisibly, until the moment the jet's motion was arrested by terrain. No emergency call was recorded. Instruments had a final, silent snapshot, altitude, attitude, velocity. Each reading will become a critical piece in understanding how an advanced fighter jet, operated by an experienced pilot, could reach a point of no return with so little warning. This is the moment before the analysis begins, the moment when silence carries the weight of consequence. The Mirage 2000 was, by design, a product of precision and purpose. Developed in the late 1970s and operational by the early 1980s, it was intended as a lightweight, multi-role fighter capable of both air superiority and precision strike missions. Its delta-wing configuration, fly-by-wire control system, and high thrust-to-weight ratio made it a formidable machine, responsive, agile, and exacting. Yet, such performance demanded an equally precise operator. Every control input, every calculation, every glance at the cockpit displays carried consequences amplified by speed and altitude. By 2017, the Mirage fleet had been in service for decades, undergoing periodic upgrades to radar systems, avionics, and engine performance. Its operational history was largely distinguished by reliability, but the aircraft's design left little margin for error in low-level flight or high-intensity maneuvers. Routine sorties for training, particularly at low altitude, required a strict adherence to flight envelopes, meticulous navigation, and constant situational awareness. The squadron assigned to this aircraft was seasoned. Its pilots trained rigorously in formation flying, low-level navigation, and high-G aerobatics. The training syllabus emphasized both technical proficiency and decision-making under pressure. Every sortie was rehearsed with precision, from takeoff checks to ejection protocols. The Mirage, while inherently forgiving in control conditions, could become unforgiving if any layer of preparation or response failed to align. Maintenance and logistical support played a silent but critical role. Routine inspections, engine checks, and system diagnostics were performed according to standard operating procedures. By 2017, the Air Force had integrated newer diagnostic equipment, enabling more precise readings of engine performance, flight control systems, and onboard avionics. Each aircraft was tracked meticulously, and maintenance logs would later become crucial in the post-crash investigation. The operational environment added another layer of complexity. Flights often took place over rugged terrain, ridges, valleys, and rocky escarpments that could appear deceptively close when traveling at high speed. Weather, while typically benign, could introduce subtle hazards. Sudden crosswinds, temperature-induced air density changes, or visual illusions over uniform terrain. Even for the most experienced pilot, these factors demanded constant adjustment and unwavering attention. In 2017, the pilot involved in the upcoming incident was well regarded, with extensive hours in both simulation and live flight. Yet, even the most disciplined aviators operate within constraints of human perception and reaction time. Training could anticipate routine scenarios, but it could not guarantee immunity from the rare convergence of speed, terrain, and system limitations. The stage was set for an incident that would test both aircraft and operator beyond their routine parameters. The Mirage 2000 was engineered for precision. Its delta-wing configuration provided exceptional high-speed stability and maneuverability, while the fly-by-wire system offered augmented control, automatically smoothing pilot inputs and preventing overstress of the A-frame. The engine, a single Snecmat M53 afterburning turbofan, delivered rapid thrust response, capable of supersonic acceleration within seconds. Yet, such performance came with strict operational boundaries. Low-level flight, particularly over uneven terrain, demanded careful management of speed, angle of attack, and engine response. The fly-by-wire system, though sophisticated, relied on accurate sensor input and pilot interpretation. Even minor misalignments in altitude, airspeed, or attitude could place the aircraft at risk. Historical maintenance logs indicated the systems were within operational parameters. No prior anomalies had been reported that would indicate a mechanical predisposition to failure. The aircraft's reliability was high, but margin for error remained narrow. Crew. The pilot was a seasoned operator with extensive experience in the Mirage platform. Hours in simulated and real-world flight had honed reflexes, spatial awareness, and decision-making under high G stress. Yet, human factors remain inherently limiting. Reaction times, perception under high workload, and spatial orientation are all vulnerable during dynamic flight scenarios. Training had emphasized both procedural discipline and tactical improvisation. The pilot would have been fully aware of the aircraft performance envelope, ejection protocols, and low-altitude procedures. However, cognitive load in a high-speed, high-altitude, or low-level environment can compress decision windows. In such conditions, even precise training cannot eliminate the possibility of delayed recognition of a developing threat, whether terrain, mechanical, or environmental. The operational environment contributed subtle but critical risk. The flight path included ridges and valleys, deceptive slopes, and rock outcrops that could appear closer than they were at high speed. Atmospheric conditions were stable but dry, offering high visibility. Nevertheless, air density variations, sun glare, or minor wind shifts could subtly alter aircraft response. Low-level flights over uneven terrain inherently compress reaction time. Pilots must anticipate changes in altitude and terrain clearance before visual cues fully appear. In this case, the region's rugged topography required continuous calculation of speed, angle of descent, and terrain gaps. Even minor deviation could amplify exponentially over the course of seconds. System and board systems provided multiple layers of awareness. Altitude, attitude, speed, and navigation were continuously monitored through cockpit displays. Warning systems existed to alert the pilot of impending terrain conflicts or system anomalies. Yet, fighter-class warning systems are calibrated for thresholds rather than prediction. A sudden combination of terrain rise, speed, and maneuvering can generate a scenario where warnings arrive too late, for corrective action. Flight data recordings, recovered post-accident, would later confirm that no system malfunctions occurred. The aircraft performed within specifications, leaving the pilot with an increasingly narrow window for recovery. In sum, the Mirage 2000, the pilot, and the operational environment were individually capable and reliable. The accident emerged from the intersection of these four factors, where high performance limits, human perception, environmental complexity, and procedural constraints converged. The final mission unfolded in real time, precise and unyielding. Takeoff had been routine. Pre-flight checks confirmed hydraulic pressure, engine thrust, flight control systems, and avionics status. The pilot ascended to a safe altitude, then executed the planned low-level navigation exercise, a standard component of operational readiness. For the first several minutes, the flight followed the intended corridor, speed and altitude maintained within nominal parameters, approaching a series of undulating ridges. The aircraft entered a section where terrain elevation rose faster than anticipated. The Mirage fly-by-wire system responded, subtly adjusting control surfaces to maintain attitude, but the pilot's situational awareness, compressed by speed and cognitive load, did not fully register the diminishing clearance. Instruments displayed sufficient altitude, yet the time available for correction was decreasing with each passing second. At approximately 30 meters above the ridge, the aircraft experienced a brief buffet, aerodynamic disruption caused by wind shear interacting with the delta wing. The pilot executed corrective inputs, banking, and adjusting thrust, but the combined effects of terrain slope, speed, and slight atmospheric turbulence left little room for error. The warning systems activated, though seconds too late to allow a full recovery maneuver. Within the cockpit, the pilot processed alarms and instrument readings simultaneously. Reflexive inputs were made, calculating angle of attack, throttle adjustments, and potential ejection. The time window for ejection was narrow. A single misjudgment could render the system ineffective. Despite experience and training, the spatial compression of the scenario eliminated viable options. Impact occurred as predicted by physics, not by spectacle. The forward fuselage struck the ridge in an oblique angle. Energy dissipated across terrain contours, and the aircraft came to rest in precise yet devastating configuration. The pilot's ejection sequence, if initiated, was delayed past the safe envelope. There was no explosion, no fireball, only the sudden cessation of motion, the silence of finality, and the immediate transformation of a high-performance fighter into a static, fragmented monument to extreme flight limits. This turning point highlights a convergence of aircraft capabilities, human perception, environmental complexity, and procedural boundaries. Each factor alone was manageable. Together, they created a narrow corridor where even optimal training and responsive systems could not avert catastrophe. The investigation began immediately, methodical and disciplined. Military crash response teams documented the site in detail. Debris orientation, ground scars, paint transfer marks, and subtle imprints in the terrain. Photogrammetry and aerial surveys reconstructed the final flight path, providing a framework for understanding how the aircraft had interacted with its environment. Flight data recorders, though more limited than those found in civilian airliners, yielded critical information. Parameters including altitude, attitude, speed, engine performance, and control inputs were meticulously analyzed. No anomalies were detected in the aircraft systems. All instruments had operated within design specifications. Maintenance logs confirmed the A-frame and engine had no pre-existing faults. The mechanical integrity of the Mirage 2000 was intact. Attention then shifted to human factors. The pilot's recent flight hours, training profile, and mission history were examined. Cognitive load and task saturation were considered, alongside physiological factors such as fatigue and G-force tolerance. Simulator reconstruction confirmed that even with an ideal response, the available reaction window was minimal. Spatial awareness was compromised not by negligence but by the unavoidable compression of time and perception at low altitude and high speed. Environmental analysis was critical. Terrain mapping confirmed a gradual rise in elevation that had compressed the effective reaction distance. Meteorological data showed stable conditions, eliminating significant weather interference, though minor wind shear was present in localized pockets. The combination of terrain and environmental factors had created a scenario where the margin for recovery was nearly non-existent. The official report concluded that the crash was a result of controlled flight into terrain caused by a convergence of human factors, aircraft performance limits, and environmental complexity. Contributing factors included low-level flight over uneven terrain at high speed, cognitive compression limiting reaction time, subtle aerodynamic disturbances from terrain-induced A-flow, narrow ejection window, leaving insufficient time for safe recovery. Institutional impact followed swiftly. The squadron reviewed flight envelopes, procedural safeguards, and training protocols. Simulator scenarios were updated to incorporate terrain convergence risk, and procedural emphasis on altitude buffers and ejection timing was reinforced. The loss underscored that even highly capable aircraft and experienced pilots remain vulnerable to extreme operational edge cases. The investigation balanced clarity with respect, framing the accident as a confluence of unavoidable constraints rather than individual error. The aircraft, the pilot, and the environment had each performed within their design and training parameters. It was their intersection that proved decisive. The lessons of the 2017 Mirage 2000 crash were codified quietly, without fanfare, in the language of procedure and training. Within months, flight envelopes were re-examined and low-level navigation protocols adjusted to incorporate greater safety buffers over uneven terrain. Simulation exercises were modified to replicate the subtle environmental pressures that had contributed to the incident, emphasizing cognitive load management and rapid situational assessment. Procedural safeguards were enhanced. Altitude awareness drills were intensified, emphasizing the importance of anticipatory action rather than reactive correction. Ejection timing protocols were reviewed and clarified, ensuring that pilots would recognize the narrow window and act decisively when required. Even technology was reconsidered. Sensor calibration procedures were refined, and instrument feedback loops evaluated to optimize warning effectiveness in dynamic scenarios. Culturally, the crash reinforced a sober truth within the squadron and the broader Air Force. Experience and machinery, no matter how advanced, cannot eliminate operational risk entirely. Respect for the aircraft performance limits and the environment remain paramount. Pilots were reminded that procedural discipline, anticipation, and measured decision-making are the final safeguards against tragedy. The Mirage 2000 fleet continued to serve, strengthened not by hardware upgrades alone, but by institutional memory. Each training sortie, each mission carried forward the lessons of 2017, a silent acknowledgement that accidents are rarely the result of a single error, but often a convergence, timing, and limits. The crash became a quiet catalyst for enhanced safety culture, shaping pilots' approach to extreme conditions and preserving lives in ways invisible but profound. Ultimately, the narrative of this incident is not one of spectacle but of consequence. The silence of the desert, the meticulous work of investigators, and the disciplined adjustments in training collectively ensured that the Air Force learned, adapted, and reduced future risk. The legacy is measured not in headlines, but in lives preserved, in procedures refined, and in the continuous dialogue between pilot, machine, and environment. In this quiet reflection, the viewer is left with a clear understanding. Aviation safety is the accumulation of knowledge, respect, and vigilance. A lesson written not in dramatics, but in precision, restraint, and unwavering observation.